Hi, this is Dan Bullard, retired electronics engineer on the front deck of my houseboat again. Hey, the sun's shining again, although it wasn't shining yesterday. I'm calling this the Doppler Effect, the wrath of Marconi. A couple of things. My wife mentioned that I forgot a couple of things. So first of all, the microphone in that setup was connected to the ACI, the analog capture instrument, and you probably figured that out from the explanation. So I used a microphone and I amplified it and I sent it to the analog capture instrument, and the analog capture instrument captured it, and the window was open from the time the person started cranking the generator. So it started going, and then once they crossed the opto sensor at the end of the track, it stopped acquiring. And so then it grabbed the center, and it just grabbed that section. It did the FFT on it. And again, it was a power of 2. So that's how we knew what to capture and when to capture. And it was, it was all coded in C++. I did it. This is before Steve Holder joined Next Test. So I did it all by myself. The only person who did any work on it was a guy named Bob Hale, who's no longer with us, and he wasn't with it either. He almost botched this whole thing because he made a little mistake in the DPS circuitry. And then Rick, of course, Rick did the generator, and of course Rick hired the people who did the booth. So that was good. Now, another thing I think I forgot was the speed of the object. We calculated the speed of the object and multiplied it by the G scale, whatever that was. So we told them what the speed of the train would be if it were not a scale train, and that was pretty cool. And the way we did that was with this formula, which, you could never find it if you went to my website. Its speed of object is equal to the speed of sound times the wavelength, which is the speed of sound divided by the shifted f, minus the speed of sound divided by the center frequency, over lambda, which is the speed of sound divided by the center frequency. Now, the shifted f, it's either one side or the other. You can take your pick. But I figured out where the center was by dividing the two edges there by 2. The space between the two edges divided by 2. So, as you can imagine, if the train goes faster, both the speed approaching and the speed leaving get further away from the center frequency. So all we have to do is find the center by taking whatever the difference is between the front and the back, divide by 2, and that's the center frequency, and then you just take one side or the other because the train was approaching or leaving at pretty much the same speed. Okay? Now, why is the Doppler shift so fucking important? Okay? Why is that? Now, you may remember a mission in space, and I love space. I'm crazy about space. There was a mission to space called Cassini and Huygens. And Cassini and Huygens launched aboard a rocket, and they were going for Saturn. And Huygens was going to land on Titan, which it's one of the few moons with an atmosphere, and they thought maybe it rained liquid hydrocarbons or something, but they wanted to see what it looked like. And there was a big protest over it. People were like getting arrested because it was carrying nuclear fuel, because there's no way that Cassini could do anything with solar panels. It just couldn't happen, right? Saturn is 1 billion miles away from the sun. That makes it, 10 times further away from the sun than the Earth is. So that's pretty bad. It's a long ways away. And so people were protesting all this. Now, Cassini and Huygens got off, thank God. And it took years, I don't know how many, it took years for them to get to Saturn. Now, it's heading for Saturn. They've got the plan. They're going to orbit. They're going to orbit Saturn, and it's going to drop off Huygens and land it on Titan. But there's a little problem. Luckily, very luckily, there was an engineer who was looking at everything to make sure that it was all going to work, or a scientist or whatever. And he took a look at it, and he realized that the radio that they used on Cassini was not going to pull it off. It wasn't going to work because it was built by Marconi, Doppler 2, The Wrath of Marconi. It was built by the Marconi Corporation. That's an Italian corporation. Remember, Marconi invented the radio. So they used Marconi to develop this radio for the Cassini thing so that Huygens could talk to, because it couldn't talk to the Earth directly. It made no sense. So Huygens was going to land on Titan and talk to Cassini, and the whole landing thing was going to be broadcast or sent to Cassini, and Cassini was going to rebroadcast it back to the Earth. And because the Huygens thing didn't have big enough antenna, but the Cassini spacecraft did. Well, somebody didn't think, because the Marconi radio that they used on the Cassini spacecraft was a match for the Marconi instrument they used on Huygens, and it was something that they used in space for satellites around Earth. Now they thought, oh yeah, it's tested in the Earth's atmosphere or in the Earth's orbit, so it should be fine. No. The approach speed to Titan and Saturn was way beyond anything that any probe or any satellite does around Earth. And so what happened is, and I'm going to let you watch this video while it happened, Cassini was going to release Huygens, and then Huygens was going to go to Titan. And in the meantime, Cassini was going to be grabbed by Saturn's gravity. Huygens was going to be grabbed by Titan's gravity. And the two were going to be pulled apart at a speed that exceeded the Doppler shift capable of being dealt with by the Marconi instruments. The Marconi radio used IF receiver, and the IF, intermediate frequency, that bandwidth there was not wide enough to accommodate the Doppler shift. And so as soon as Cassini and Huygens separated and got a little bit apart from each other, the Doppler shift would exceed that radio's ability to capture the data from Huygens. And so Huygens would be lost. The data would be lost. Now, it was supposed to get like 700 pictures as it landed, so we would have lost them all. But in addition, it turned out that there were two transmitters on the Huygens spacecraft because they didn't have enough time to relay all the data up, 700 photos, up to Cassini with one radio. So they used two radios. One radio failed en route. So this scientist was able to convince JPL they had to change the way that the orbit happened so that Cassini and Huygens would not be pulled apart so violently, and that they would not exceed, the Doppler effect would not exceed the radio's ability to keep on track through the intermediate frequency, and it would be able to get the data from Huygens as it landed. But Huygens, one of the radios failed on Huygens, and so 350 of the pictures taken by Huygens were lost. So that's a $3.26 billion project So that could have been a total bust if somebody hadn't looked at it and figured out that the Doppler shift was going to stop this mission in its tracks. But luckily, this scientist was able to look at it and figure out that the Doppler shift exceeded what the Huygens and Cassini pair could do, and so they replanned the mission while it was en route. It was like out past the orbit of Jupiter, and they said, hey, let's like reprogram it to do something else. So they had to reprogram the mission while it was in flight, and they got it to work. And you know, the pictures were pretty good, but sure as hell would have been bad if they didn't get any pictures. And you know, say, well, you know, Cassini might loop around Saturn and come back and get some more data from Huygens. No, Huygens is so cold the batteries froze up almost instantly, and so not long after Huygens landed, it was a pile of junk. And so yes, we're leaving piles of junk all over the place. So on Titan, there's a pile of junk that doesn't work anymore because the batteries froze up and nothing works there anymore. So the Doppler shift is a big deal. Every time SpaceX launches something into space, when you're watching those images on SpaceX on YouTube, those images have to be sent down with the Doppler effect in mind. It has to be able to track that. Now, I don't know whether they move the local oscillator or whether, I don't know how they do it, but it's pretty trippy. The Doppler effect is a big deal, a really big deal. Satellites, spacecraft, airplanes, cars, your phone has to deal with it. When you're driving down the road and talking on your phone, you have a Doppler shift between your phone and the cell tower. And you might be approaching the cell tower and you might be driving away from the cell tower. And the cell tower has to be able to accommodate that shift. Now, if you go too fast, would it exceed it? Would it exceed the limit? It might. And, you know, one of the tricks I thought of for getting around the government tracking you is to take my phone and put it in a package and FedEx it to somebody else. And so they would think I'm in another town because my phone would be there, but I'd be somewhere else, right? But during the flight, it would probably work. People can talk on phones on planes, even though they generally don't want you to, because it will interfere with the electronics. But the Doppler shift is a big deal. And Bob and Doug, sorry, Bob, you guys had it wrong. It's not, you see it before you hear it. That's not how it works. Anyway, once again, from the river, this is Dan Bullard. See you later.